I once had a student on exam that had the sulfates going right through the beakers. Don't do that. Okay, they have to go through the salt bridge. Okay, now how about the negative charge on the nickel? So all positive ions migrate that direction. So positive nickel goes to the right, positive iron goes through the salt bridge to the right, and also the positive potassium goes to the right. Okay, since there are 6 ions, each ion should have an arrow on it. So a little complicated, but hopefully not too bad. Okay, terminology. The iron half reaction is oxidation from 0 to +2, and oxidation occurs at the anode. And nickel is reduced from +2 to 0, that's the cathode. Okay, how about the cell voltage now? So I just copied the iron 2. By the way, I know this is a mistake here. Why don't you correct it? This should be a +2. I know it says equal to, so why don't you correct that in your notes? And I guess the same thing up here on the half reaction. For some reason, I didn't do that correctly, so correct those. Okay, so I copy the iron half reaction as given. The nickel's the reverse of the chart, so I reverse the sign and make it a negative 0.250. Okay, algebraically add them together, and this positive here should make you feel good, because a positive sign means every arrow is in the right direction, and this is the spontaneous reaction. Okay, so the little man up here, he's grabbing onto the iron, which means he's getting electrons given off by the iron. So this is the negative post, and this will be the positive post. So hopefully you'll feel pretty good about these cells at this particular point right here. Okay, now I'd like to show you the battery that starts your car. It's called the lead acid battery. If I had more time, I'd go through the chemistry of it, but here's the key thing I want you to get out of this battery. Okay, first of all, I did a calculation once, and I found out that the lead acid battery only has a voltage of 2 volts. Wait a minute, I thought they were 12-volt batteries. Well, so far, here's the deal. We've been calculating what's called the voltage per cell. Notice that your car battery has 1, 2, 3, 4, 5, 6 cells. These are connected what's called in series, which means 6 times 2 means you get 12 volts. Now, if you have a motorcycle, you only have 3 cells. Okay, 3 times 2 means you have a 6-volt battery. Kind of cool, isn't it? So all those other numbers we got before, that's the voltage per cell. You can take a lot of cells and put them in series, and you can get a hell of a lot of voltage. I once had a friend who was in the used battery business, and he decided to build his own electric car. What he did is he took the motor out of his car and put 50 of these lead acid batteries into the hood of his car, and then 50 in the trunk. So he had 100 batteries. 100 in series times 12 means he had a 1200 voltage car. He once took me on a ride on it. I couldn't believe how fast it was, how quiet it was. It was really fantastic. Slight problem. It was also one of the world's heaviest cars, which means he had to put special shocks on the car, and he also had to put special brakes on the car. The point I'm trying to make is the lead acid battery is not a good way to have an electric car, mainly because the batteries are so darn heavy. You don't get much electricity per pound, and this is what kind of slowed up the origin of the electric car. And the Tesla's so good because they don't use lead acid batteries; they use lithium batteries, which are really nice and light. So the point is that you can get a lot of voltage if you put these cells into series with each other. You're now going to look at probably the most important battery in this unit. It's called the concentration cell. Now, the concentration cell consists of the same metal on both sides. That's one thing sometimes students have recognizing on my exams is how do you know you're dealing with a concentration cell? The answer is it's the same metal on both sides. That's the tip-off. So notice copper metal and copper metal. Okay, so same metal on both sides. And you have the same solutions on both sides. So you have copper +2 and copper +2. I'm going to ignore the negative ions for the moment. Okay. Now let's say, for the sake of argument, that the right-hand copper is the one that's going to give off the electrons. So notice I've got the blue arrows going from right to left. So let's just use that for sake of argument for the moment. Okay. Now, if that's the case, let's look at the 2 half reactions that take place. Okay, so on the right-hand side, I have the copper metal giving off the electrons and forming copper plus 2 ions. By the way, from now on, we're going to worry about concentration. So when you have ions, notice I've written 1 molar in parentheses. Now, if the electrons are going to go from right to left, that means the reaction, the half reaction on the left-hand side is the copper plus 2 ions are going to be attracted to those electrons, and they're going to plate out as copper metal. Okay, now I'd like to add these two half reactions together. Okay, so I've copied the left-hand half reaction, and underneath I have the right-hand half reaction. Now let's cancel out what is the same. So the electrons cancel out, the metals cancel out. Now I know that the ion concentration should cancel out, but don't cancel them out. So summing the two reactions together, we get the overall reaction: copper plus 2, 1 molar, goes to copper plus 2, 1 molar. Okay, now here's the deal. Look at the voltage of the cell. So copper plus 2 going to copper ions is a plus 0.77 volts. Okay, locate that half reaction with me. So it's kind of about 4 or 5 down from hydrogen. Copper metal to copper plus 2, okay, is a negative, but the top one I reverse the sign, and the bottom one is the sign given. Now, notice that the voltage there is 0, which means I just wasted 5 minutes of your time. Berg, what are you up to? Okay, now, does anybody have an idea how we could doctor up the cell and get some voltage out of it? Hint, instead of having 1 molar on both sides, how about if we have, any suggestions? How about different concentrations? Which leads to the next chart. Okay, so the idea is maybe we can get voltage out of a concentration cell if we have different concentrations. Now, the secret to success, so notice the left-hand compartment has 1 molar copper, the right-hand compartment has 10th molar copper, so there's a hope that maybe, just maybe, we can get some electricity out of this thing. Now, the secret to success is to look at the orange arrow. Let's pretend for the moment that there's no break between the two beakers. It was open. If it's open, what does nature like to do? Nature likes equal concentrations. So some of the 1 molar copper would flow from left to right to the 10th molar copper and try to equalize the concentrations. Does that make sense to you? Because that is a secret. Now notice I've written the overall reaction below in black. So the 1 molar copper would be the reactant. The 10th molar copper would be the product. Okay, so we're trying to get rid of some of the 1 molar, there's too much, and try to make some of the 10th molar, which is too little. Now do yourself a favor. Underneath the overall reaction, draw an arrow downward under the 10th molar copper. That didn't work, okay. And draw an arrow upward on the 0.1 molar copper. Okay. Because the overall reaction says that the stuff on the left is going to be used up, and the stuff on the right is going to be produced. Okay, now here's the tricky part. We know what the overall reaction is supposed to be, but how can this happen? Look at the right-hand compartment. We're supposed to produce extra copper plus 2 ions. How can that happen? The answer is, how about if the copper metal were to dissolve and form copper plus 2 ions? And so look at the half reaction I've written below. The copper metal is going to produce copper plus 2 ions, which originally is 10th molar. Now, to have a balanced half reaction, it's going to produce electrons. Where are those electrons going to go? They're going to flow through the wire. So that's how the right-hand compartment can produce extra copper plus 2 ions. Now look at the left-hand compartment. We're trying to get rid of copper ions. They can't leak anywhere. So what will happen is the copper plus 2 ions on the left will be attracted to the electrons coming in, and so look at the half reaction below. It says copper plus 2 ions, which are 1 molar, will pick up electrons to become copper metal. So notice these two half reactions do exactly what we're supposed to do. The right-hand one will produce more copper ions, and the left-hand one will use up those copper ions. Okay, so now let's look at the cell voltage. So, by the way, just as a double check on this, okay, I've always noticed this at the overall reaction arrow and the electron flow are in the opposite direction. It's probably worth memorizing. So you get the overall arrow by getting by the what nature likes to do, and that is get equal concentration. So that's why I went to the right. Okay, and I've always noticed that if you look at the arrow of the electrons, it's in the opposite direction. So that's kind of a double check for you to do. Okay, now let's look at the cell voltage. Okay, so the left-hand compartment is the opposite of what's on your chart. So if you look on the chart, copper 2 to copper metal is a flip of what's on the chart. So that's going to be a positive 0.337 volts. You change the sign. And the bottom half reaction is a copy of what's on your chart. So it'd be negative 0.337 volts. And again, we get zero voltage. Now, here's something I haven't talked about yet. You notice a little zero next to the E? E0 means standard conditions, voltage under standard conditions. So look at your chart again. You notice that this is all E0. These are the voltage you get under standard conditions. Now, what are standard conditions? Standard conditions are the concentrations are 1 molar and the temperature is 25 degrees Celsius. Now, the darn trouble is, if you look at this cell, this concentration cell, the concentrations are not both 1 molar. So what to do? No one knew for years how to do this calculation until, next chart, a fellow by the Nernst came up with a Nernst equation. Now the Nernst equation reads like this. It is good for calculating the voltage of any cell, but you first have to calculate the standard voltage of the cell. So our chart is still useful. Okay, so we're going to get the voltage of the cell, but one of the things we need is standard voltage. So just like you've been doing all this time. Now here's the next part of the equation, minus RT divided by Fn times the log of the mass action expression. Now let me go back to this RT over M. R is your old friend, the ideal gas law constant. It gets all over the place in chemistry. It must be one of those universal truths. T is the temperature. So therefore we can change the temperature and figure out the voltage of the cell. Okay. F stands for Faraday constant. Now, so here's what happened a few years ago. Some chemists said, you know what? Here are three, if we keep the temperature at 25 degrees Celsius, which is kind of normal room temperature, that means these three things are all constants. R is a constant, T is a constant, and F is a constant. So why don't we take these three constants, figure out their value, and their value turns out to be 0.06. So we're going to use 0.06 as the value of those three constants from now on. And N is kind of tricky until you get used to it. N is the number of electrons that are being transferred between the two half reactions. If you look back at the cell we're dealing with, N is equal to 2 because 2 electrons are being given off by one and taken by the other. And then the log of products and reactants, that's the log of the mass action expression. Okay, so now I want to apply the Nernst equation to our concentration cell. So the voltage of our concentration cell is equal to, first of all, the E0 is 0 volts. For a concentration cell, E0 is always 0. Why is that? Because E0 means you make the concentrations 1 molar. If they're both 1 molar, no voltage. Okay, here comes the next part of this. Minus, okay, 0.06 is the constant we're going to use from now on, divided by, where did I get the 2 from? 2 electrons are being transferred between the two half reactions, and then the log of, now this is where you want to look at the total reaction and its products of reactants. So the product was the 10th molar copper, and the reactant was the 1 molar copper. Okay. So look at those numbers and see if it makes any sense how I plug these into the Nernst equation. Okay, any questions on it? You see where all the numbers came from?